think we want to switch this up just a little bit because I think that you guys can follow this just as well if it's all there for you at once, as opposed to if we do this slowly. So here we got the blank page, and I want to add things in as we go. Okay, so here I'll pull over my written page. What I'm going to ask you to do is add into this picture. So as we're adding into this picture, we've got this flow of charges. I've color coded this already. I wrote it so that I got red protons staying put. We know that we're going to put our protons as being staying put because if this was like copper wire, the nuclei of the copper are not going to be flowing. It's going to be the electrons that are flowing. So I'm going to ask you to have arrows, these vector arrows, attached to the negative little electron charges that are allowed to move. Those are the mobile charges. We've learned about that in chemistry. We learned about it in grade 9 science. This is something that we should be well aware of. It's electrons that really flow, not protons. And when we talk about flow, we're talking about a flow rate, like a river. So, like when a river flows, you talk about how many liters flow through that river per second. And I know that a lot of text just came up. So people that are slow writers, like, oh my gosh, this guy never uses slideshows. And I'm not using a slideshow. I'm sticking to handwritten notes. But we're just talking through it a little bit faster. Don't worry, I'm not going to get away from you. I'll wait for people to catch up. This idea of a flow rate, though, reminds me of a river. With the river, it's liters per second that flow through the river, or gallons, or whatever, some volume per second. When it comes to charges, we talk about the amount of charge that flows through a conductor per second. But we don't talk about it in liters or gallons. We talk about these charges as being clusters. In fact, they're huge clusters. When I talk about a coulomb of charge flowing through a wire every second, a coulomb is 6.24 times 10 to the power of 18 elementary charges. That is a lot. I mean, I have a regular word that I use for 10 to the power of 9. 10 to the power of 9 is a billion. This is 10 to the power of 18. This is a billion billions. This is a lot. And so I don't have a nice fancy word like billion for 10 to the power of 18. I just say 10 to the power of 18. And specifically with the electric charge flow, I talk about charges by the coulomb. And people say, well, I have a hard time accepting why I would do that. Well, you accept it with eggs, right? When you go and buy eggs, you buy 1 dozen eggs. And nobody questions, how many eggs are in a dozen? 12. What a weird number. Why 12? Babylonians probably, right? It's divisible by 3, it's divisible by 4, it's divisible by 6, it's divisible. Now, this is great. 12 is a good number. That's why they chose a dozen, right? I'm sure that there's some historical reason other than that, but it is a great number for chopping up your merchandise. It turns out that with coulombs, it actually ends up working with all of our other units. So it meshes with our SI units. And when we talk about the number of coulombs that flow per second, we're talking about amps. So coulombs per second, we call amps. Now, we've dealt with amps before when we talked about current in grade 9 science, but current is a flow rate of electricity in amps. Coulombs that flow through a point in a circuit per second. Now, amps, when we're writing them as units, just capital A. When we're talking slang, we call them amps. Really, we know it's somebody's last name, ampere. But nobody, when they're on an electrical job site doing up wiring, nobody says, oh, I'd like to grab my multimeter and measure the amperes. They measure the amps, right? And so here I am freely using the slang because everybody uses the slang. It's so ubiquitous, right? So we're going to use the slang and be okay with that. I got to get a little bit of head nod from the class because I'm watching people's hands finish writing. Can I kind of start to move on slightly? I'm trying to not just give you, things straight. I'm trying to explain things, but also fill airtime while you guys write. So as I think down this page, I'm going to start doing a little bit of a reveal. As I think down this page, what we're talking about here is a quantity of charge. We use capital Q to talk about our quantity of charge that's flowing through a circuit. And we pretty much always use capital Q. You might see some people use lowercase q for quantity of charge. That's fine. That's a style issue. But I'm going to try to remember to use capital Q. Delta T, same as in kinematics though, same as in sound and waves. It's just how much time goes by. That'll be measured with a stopwatch if you like. But if I wanted to calculate what the current is, and you might remember back to your grade 9 days that we use the variable I for current. So the variable I for current, that's not new from back in the day. And we're still using amps as the unit for current flow rate. We're just kind of introducing this new idea that current flow rate is really the quantity of charge that flows through a circuit per second, the number of coulombs per second. And a coulomb is a bundling of charge. And once upon a time, and you could probably look up on my bookshelf over there, once upon a time, somebody gave me a peanut butter jar because they thought that they needed a visual for what a coulomb was. And so if you looked up over on my shelf, you'd see a peanut butter jar full of golf balls, and each of those golf balls has a minus sign on it. And it's supposed to be like this visual representation. I think it's got a green lid. It's right up over there in the glass cabinet. Each one of those golf balls has got a minus sign on it. And that was supposed to be like a visual representation of what a coulomb could be like, you know? Only obviously, if you look at my peanut butter jar full of golf balls, is there any way that there's 10 to the power of 18 golf balls in there? No. A coulomb is a lot. It's a lot of charges per second. That's why we had to cluster it as a coulomb, because nobody's going to sit there and count individual electrons any more than you were going to sit and count 10 to the power of 18 golf balls, right? I mean, in fact, that's the whole challenge behind the that carnival game where you have to guess the number of jelly beans? That's hard because it's hard to count a lot in one jar, right? So we call it by the coulomb. Again, I'm watching the room on this as I do the reveal. We think about circuits like this one here. And actually, you know what? I think I want to take a second and actually draw this circuit. So you guys, I just gave you the sneak peek, but when we talk about drawing these circuits, we talk about drawing a source, and then that source gets attached to a switch. Usually we almost always have a switch to regulate our circuit. And in this case, I'm going to use a light bulb for my load. And then, of course, that light bulb would be back connected to the source, but I've got an ammeter connected here. And those that remember as far back as grade 9, remember connecting ammeters. You remember if they were connected, do we say series or parallel? What does it mean to be connected in series? Do you remember? Yeah?
Series is like everything's connected?
Yeah, well, it's connected so that it goes in one side and out the other. So this is an ammeter connected in series. And that current's going to go back to the source. That light bulb is the load, and the ammeter is in series with the light bulb. In other words, the current had to go in one side of the light bulb and out the other, and in one side and out the other of the ammeter without branching off and taking a separate pathway. When we connect voltmeters to measure voltage, which we haven't actually talked about, but here's a device for measuring voltage, we connect them in parallel. And to be connected in parallel means to introduce an alternate pathway. So we have a pathway that goes to the light bulb, we have a pathway that could go through the voltmeter, and we're connecting it in parallel to provide that alternate pathway, and that's how we measure voltage, okay? In terms of physically how we connect it. Now, in terms of what's flowing here, in the original sketch, you can go back in the video if you want to go back in the video, but I'm going to add things in. You notice that we have a positive terminal and a negative terminal for every DC power source, for every battery. So if you have like a D battery or a AA battery or a car battery, there's a positive terminal and a negative terminal. It makes sense that electrons would flow out of the negative terminal. That seems like a reasonable labeling. Here's the kooky thing. The kooky thing is that around the turn of the last century, we actually got physical evidence of electrons' existence. But chemistry had already started the science of being chemistry. And physics had already started the science of being physics. And we kind of discovered concrete evidence for the electron partway into the story. You believe that? And so people had already defined this thing that we call conventional current as flowing from a positive terminal before we were really sure that it was only the electrons that were mobile. Isn't that kind of annoying? Ton of textbooks got written, people published, they wrote letters, like all this sort of stuff. Everybody was very excited about it. You can imagine you just discovered electricity. It's like discovering fire, right? Everybody's talking about it.
Yeah.
And so we got this idea of conventional current flow that came out of all those conversations. Sadly, conventional current flow is going the wrong way. You guys see that? Here's the great thing. The flow of positive charges going this way and the flow of negative charges going the other way is actually equivalent. In other words, just as many electrons would be flowing as protons would be flowing in order to sustain the same current. It's just that physically flowing protons is stupid because that would mean that you're ripping nuclei out of atoms in a battery and sending the nuclei through a tube. That doesn't make sense. Ripping electrons off of the valence shells of like an electrolyte or the electrodes, that makes sense. And maybe you'll learn a little bit about that in chemistry with electrochemical cells reactions. But it really is the electrons flowing. Unfortunately, all the textbooks got written before we figured this one out. And so we have this dilemma in electrical circuit analysis where we talk about conventional current all the time, but it's going the wrong way. But that's okay because it follows all the patterns. Okay, so I'm just letting you know about that. It's like a historical quirk that we're going to talk about conventional current, which we label as I, which is this like slightly false idea that positive charges are in motion. And so I got a little blurb about it here. Let's write this little blurb down before we go over to these symbols. Conventional current flow, that's this false idea that positive charges flow from the positive terminal. Electron flow, which is the physical reality of things, is that negative charges actually are flowing from the negative terminal. Now, you folks, as physicists, you guys are going to be able to roll with this. I got family that have done an electrician's program, electrical technician's program. Now, whether or not they ever have to be confronted with this, may be questionable. If you're going to go be a physicist, you should know the difference between the two. If you're going to be a home electrician or a person that does the wiring in someone's home, you probably won't ever care. If you're going to be a physicist, you almost certainly will care. Now, in terms of symbols, because we have to have a visual language for drawing our circuits, I've already drawn an ammeter. I've already drawn a voltmeter, A and a V within a circle. Light bulbs, I put a single curl loop inside of a circle. That's a common way to do light bulbs. Another common way to do light bulbs is an X in a circle. And if you've done architectural drafting, show of hands, anybody who's done drafting class. Yeah, one, couple people. I bet you the software that you use uses the bottom diagram for light bulb locations, because schematic diagrams for architecture typically does. Am I right? Yeah? Okay. So in our circuits, we're going to use the single loop. This matches actually with what was done in your grade 9 class, I suspect. Again, nod of hands or heads, yeah? Loops in a circle? All right. Other things like a motor, for example, might just be like an M inside of a circle. Now, if we have specific symbols that we're going to use, I'll let you know about them. But here's one, and I'm almost 100% positive that everybody saw this. This is the symbol for a resistor. A resistor, unlike a light bulb, doesn't glow, but it does resist the flow of electrons and it dissipates electrical energy. Yes? Yeah, sure. Now, this is like your basic grade 9 circuit. If I wanted to do a calculation with this, we're going to have to pull out some of our equations from earlier. Thank you very much. And so this question says, if 5.0 times 10 to the power of 20, notice the numbers are big, electrons pass a point on a circuit in 2 minutes and 40 seconds. If I say 2 minutes and 40 seconds, I'm going to allow that 0 over the 40 seconds to be significant this time, okay? Now, the reason I'm writing it as 2 minutes and 40 seconds rather than 2 points, whatever seconds, is that we have to acknowledge that people often will time devices using like a stopwatch or something like that. And so I'm just going to remind us of something we probably learned in grade 7 or 8 or something. I can't remember when I learned it for the first time. But if I got to write down what the time is, then the time is going to be 2 minutes and 40 seconds. But that really means 2 times 60 seconds plus 40 seconds. And so we got to be able to convert this over to an SI unit of just a pure second. No mixed values of minutes and seconds. And of course, 2 minutes and 40 seconds, I think one of our local math teachers would lose her mind if you wrote it as 2.4 minutes or something like that, right? 2 minutes and 40 seconds is not 2.4 minutes. Like, I would lose my mind too. But the number of times I've heard people rant about this in the math science office, oh, these people, they don't understand that time isn't metric. Not, I don't want to name names. We're all friends, right? But it upsets us, right? Because it's something that we should know and from elementary school. Now, when it comes to 5.0 times 10 to the power of 20 electrons, we got to be able to convert it into coulombs. So there are 6.24 times 10 to the power of 18 electrons per coulomb. Writing it like this, the number of electrons per coulomb, helps me to think out how I would turn this guy into a coulomb's value. Look, units-wise, because I know electrons isn't really a unit. Electrons is just what we're counting. But if I have electrons divided by electrons per coulomb, can you guys see that the units in the denominator are going to invert and put coulombs in the numerator? And so that tells me that if I want to know how many coulombs there are, I'm going to have to take the number of electrons divided by the number of electrons per coulomb. That would tell me how many coulombs I've got in my pocket, right? So here's the math on that. A little pre-thinking on the units. But if I wanted to get blank number of coulombs based on what we were given, 5 times 10 to the power of 20, I would take the 5 times 10 to the power of 20 divided by 6.24 times 10 to the power of 18 electrons per coulomb, or elementary charges per coulomb. I really shouldn't say electrons per coulomb. I should say elementary charges per coulomb, because there'd be just as many protons, which is another elementary charge, in a coulomb of protons. It's only an electron if I put a negative sign above the E. An E without a negative sign really stands for elementary charge. Okay. All right. So if I do that math, I get 80.128 coulombs. And here I am. I'm trying to fast forward things just a little bit because I know that we could plug this stuff into our calculators. Be careful. Make sure you can do this, because people often get tripped up with scientific notation. Don't forget to put that value in brackets. Otherwise, your calculator will reject you. Okay, we want to make sure that things don't get messed up. It would end up being like something 10 to the power of 38 or something like that. Okay, make sure you put it in brackets. So that's a data entry thing. Now, people often would like to have like a formula for something like this. So actually, there is a formula for something like this. The charge that we're talking about would be the number of electrons, or number of elementary charges, divided by the number of elementary charges per coulomb. And so sometimes you'll see people write the same formula as Q is equal to N over 6.24 times 10 to the, 6.24 times 10 to the power of 18. That's an alternate way that I've seen this many times. And so that's what I've got here. Q equals N over 6.24 times 10 to the power of 18 elementary charges per coulomb. I'll put a star beside that because that's something that we should be able to do to figure out how many charges there are. So let's take stock of what we've got. If I want to know the current, at this point, I've got the number of charges that are going to flow through this circuit. I know how long the circuit is turned on for. And then that brings me to this. Well, I is equal to Q over delta T from the top of the page, right? And we sub in our values. And we get it as 0.5 amps. And much like Indiana Jones, this does not shock us because we're scientists. Okay. Now, if you get a half of an amp and it does flow through you, it will shock you. It will upset you a fair bit. Half an amp is not a good feeling. You can do your research on that, what half an amp going through your body would do to you. But we'll leave that for now, okay?